In our last video, we covered installing and navigating FPS. Now, we're diving into one of FPS's most powerful capabilities, data collection and management. FPS makes collecting, analyzing, and saving splice data simple and efficient, helping you optimize your workflows and improve splice performance. To start, open the Data Collection module from the FPS module menu. After selecting it, a tab appears along the top of the main window. This tab can be either closed or popped out if you'd like to resize or view multiple windows at once. Just below the Module tab are the data control options. Under the File menu, you can create a new dataset, save your current dataset, load old datasets, and export your data to Excel for further processing. The Options menu allows you to toggle between standard and high-quality image collection from the splicer. The Data Collection module has 4 sections. 1. Main. The primary data collection activity takes place here. 2. Data. A detailed breakdown of collected results. 3. Loss estimation for fine-tuning splice loss estimation parameters. And 4. IPA Data, used for analyzing rotational alignment performance. You can collect data points individually or automate collection as you use the splicer. If you haven't already, set a save location. If not, FPS will prompt you each time you collect individual data points. To use auto collection, a save location must be set. Click the Start Auto Collection button and a File Explorer window will open for you to name and save the dataset. Once set, you'll see the dataset title listed at the top of the page. FPS offers 2 different types of screen capture. Data Screen Cap, which saves the splicer's screen along with any firmware overlays like text and borders, or Live Screen Cap, which captures the splicer's screen exactly as displayed but in higher resolution and without overlays. Each splice image is automatically saved in the chosen save location. If a save location isn't set, images will be discarded. Below the screen capture options, you'll find radio buttons for choosing what data is collected. If the splicer is connected to a power meter via GPIB, choose GPIB loss measurement option. If the power meter is connected via USB, select the USB loss measurement option. If you only need estimation data, select Collect Data Only to forego loss measurement. The Loss Estimation tab is where you'll fine-tune estimation settings to match the actual measured loss from the splice. At the top, you'll see the splice loss data, the loss estimation parameter values, and a graph comparing estimated loss versus measured loss. At the bottom of this tab, you can adjust sensitivity settings to refine estimation accuracy. Now, let's return to IPA data. IPA stands for Interrelation Profile Analysis. It correlates a fiber's side view profile with its angular position, which is useful for analyzing internal structures like stress rods, multi-core fiber cores, or geometric fiber facets. To collect IPA data, enable the Collect IPA Data checkbox on the main section. FPS will download and save rotational alignment data for each splice. On the IPA Data tab, you'll see a graph displaying rotational alignment data, a table of calculated crosstalk values in decibels or degrees, and the option to view alignment data before and after splicing. The next section we'll take a look at is the Download/Upload module. This is your hub for managing your splicer settings, splice mode parameters, and distributing them to other machines. In the top left-hand corner, you'll see the File option. This simply allows you to save a mode or range of modes as the default input values whenever you open the program in the future. The Download/Upload module has 2 pages, one for handling splice modes and the other for handling splicer machine settings. On the Modes page, you can download a single splice mode or select a range option to download all splice modes within a defined mode number range. After entering your values, choose Receive from Splicer to pull the parameters into FPS. From here, you can view the settings of a particular splice mode, save the settings as a file, export them to Excel, load another previously saved file, and upload parameters back to the connected splicer. Similarly, the Utility page allows you to download the splicer settings, save them, export them, load other settings, or send them back to the splicer. The last of the data management modules is the OCB Reader. This module is unique to the LZM splicer and communicates with the LZM's optical control board, or OCB, which plays a critical role in system operations. The OCB manages laser control systems, operates the optical motors, and handles the LZM firmware, as well as performing many other system functions. Because of these unique considerations, the OCB Reader Module provides a direct interface to track, monitor, and control OCB functions, giving you a real-time dashboard for assessing system status. To use the OCB Reader, click the Start button to begin streaming data from the splicer. Once streaming starts, the splicer status panel at the top of the screen will display real-time monitored information, allowing you to quickly assess the machine's performance. Now that OCB streaming is active, you can interact with key system controls, including mirror and focus adjustments, laser controls, and beam path modifications. You will always have the option to go home, which resets the optical motors to their home positions, or update motor positions, which reassigns the current motor positions as the new home position reference points. Depending on your splicer model, you may or may not see the toggle beam director option. For LZM models where applicable, this function allows you to switch between the fusion beam path and the ablation beam path as needed. One important note, while the OCB reader allows for full motor movement, clicking Update Motor Positions will override the stored home positions with the current motor positions. If you're performing a beam alignment procedure as outlined in the instruction manual, this is the correct way to reset the home positions. However, if you're not aligning the machine, resetting the home positions will disrupt the existing beam alignment, leading to miscalibrations and poor splicer performance. If you accidentally click the Update Motor Positions, you will need to realign the machine's beam path following the instructions in the user manual. Inside the OCB Reader module, the exact options you see will vary depending on your splicer model. For example, in the case of the LZM 125A+, you will have path controls for adjusting the top and bottom mirror positions as well as the beam focus position, and live positional readouts for both the front and rear beam positions. If you look at the laze box, you can set the duration for a laser operation. For example, if you enter 5 seconds and press fire, the shutter will open and the laser spot positions will be displayed in the center window. The blue circle represents the reading from the rear thermopile, while the green circle represents the reading from the front thermopile. By default, power readings from the thermopiles are displayed in watts, and the coordinate system is set in millimeters relative to the center pile. When the beam indicator spot approaches the center circle, the coordinate system will automatically double in size, as will the spot indicator itself. This helps with precise positioning. Because the 125A+ includes motorized mirror controls, it's possible to move the upper and lower mirrors using the on-screen adjustment options. To do this, enter the desired step value in the text box between the adjustment arrows, then click an arrow to move in the desired direction. By default, steps are measured in microns, but you can switch to steps mode if you prefer. If the laser is firing, you will also see the beam position indicators move in real time as you adjust the mirrors. Since the splicer includes an ablation beam focuser, you could also adjust the beam focus using the same method. This adjustment changes the spot size of the laser on the fiber. If I need a very small or a very large spot size, I can fine-tune the beam focus accordingly. Now, let's take a look at the Charts tab. Here, we have a graphical log of the laser readouts across time. In the top graph, you'll find front and rear thermopile X and Y position readings, a reference value from the beam sampler, and a set point reference measured in bits for power comparison. The bottom graph displays a detailed power reading from the front and rear thermopile, as well as the laser temperature monitor. Typically, the operating temperature range for these lasers is between 41 to 43 degrees Celsius, but this may vary depending on the laser model and environmental conditions. When performing beam alignment, it's best practice to save the OCB graphs from the procedure for future reference. This allows you to compare past and current alignment data, ensuring proper calibration. To save the graph information, simply click Save Data. This will generate a CSV file, which can then be opened in Excel for further analysis. Finally, let's take a look at the Firmware tab. Here, you can view the current OCB firmware version, reset the OCB, or upload new firmware versions when updates are needed. The OCB Reader Module provides full control over the laser splicer's optical control systems, allowing for precise beam adjustments, motor control, and real-time performance monitoring. With these tools, you can ensure that your splicer operates with maximum accuracy and efficiency. The FPS data collection and management features allow for easy data logging, splice loss estimation, and advanced alignment analysis. In our next video, we'll explore splicer control in FPS, covering how to interact with the splicer and optimize real-time performance. Thanks for watching, and we'll see you in the next lesson.